Yeah, hi everyone. I'm Ansgar. I am a researcher at the Ethereum Foundation. And as of a couple months ago, I'm co-leading together with two colleagues of mine the Ethereum L1 scaling effort within the Ethereum Foundation. That's together with Tim Bako and Marius van der Weijden. And so I thought it would be a good opportunity today to explain a little bit how maybe this is a bit slanted towards how I personally kind of see the individual work streams on that topic and how they all basically are ideally going to fit together to help us really scale Ethereum. First thing I wanted to briefly point out is the different timescales on which this work is happening. I think there's really three main timescales. The first one is the type of work that a lot of the people here in the room are very familiar with, are really focused on, which is the kind of all the things that don't need changes to the Ethereum protocol, don't need hard forks. That's performance improvements in the clients, new database types, improvements to sync, all these kind of things that really make a big difference for Ethereum, but don't need a hard fork, and so can happen on shorter kind of iteration cycles. Then there's the things that do need hard forks. So that's basically the medium time scale. That's anytime you are improving the overall, like the scaling level. In our case, we're talking about scaling by basically changing really the rules of the system. These usually have like maybe, I don't know, like all in a 1 year kind of cycle length. And then you have the very occasional, like really big kind of paradigm shifts to how Ethereum operates. So you can think like the merge was one of those cases. On the scaling side, we now have a really exciting one on the horizon, which is our move to real-time ZK EVM, which will be another one of these real like paradigm shifts that unlock a lot of extra scaling, but also is like a multi-year project. What you should not like make sure to not think of this is that you basically like we're only doing this short cycle work now, and then we'll move on and only do the medium cycle and then only do the long cycle work. Instead, basically, if you think of it as a timeline and try to like map out the next 3 years roughly, it's really just that all of these work streams are happening in parallel. Like there are people in the EF, in the clients, in the ecosystem that work on all three of these different activities, and they'll basically just like, it's more the iteration loops, basically like how quickly do these produce results, is basically on a different speed. And it's a fun exercise if you try to like map out the next few hard forks. I mean, don't quote me on this like in 2 years, but I actually think that I-star, like the hard fork 2 after Amsterdam, is the first candidate that might already be when we bring ZK EVM to mainnet. Could be like 1 or 2 later, but I really think this might already be where we have at least a shot of delivering this. For my talk, though, I will focus really on this medium timescale, because that's really, I think, that where I'm mostly focused on internally. We have people, if you want to reach out to maybe Marius or Pari, that really kind of had our kind of short cycle work. And then on the ZK EVM in particular, we have Kev and Justin that really kind of focus their energies on that. I will talk on the medium term because I think that's actually also quite exciting, and I really think there's a particular pattern that I'm going to try to convince you that's underlying like most of the work happening there. One more basically specific zoom in here. I'm not going to talk about all the feature work around scaling, but I want to specifically focus on just simple full nodes. So there's all different types of Ethereum nodes out there, of course, and like as we run the chain faster and faster, they'll all run into different challenges. But where the main kind of core of scaling is really just on like block verification inside of normal full nodes, right? And that also means if I say just block verification, that means I'm exclusively right now in this talk focused on what we call the burst constraints. So I think there are really 3 main resources in Ethereum, in Ethereum nodes. That's the bandwidth that you use for downloading the blocks. It's the compute for verifying the block, and then it's the disk, basically like how quickly can you basically get data from and back to disk. And so all of these basically constrain how quickly we can verify blocks as they come in. There's the entire separate kind of branch of work of how can you make sure that as the chain kind of runs for a while and accumulates load, how do you keep running it fast? Again, out of scope for this talk specifically. And then one more point that I wanted to point out, because sometimes people are a bit worried about this. None of this is about saying, well, we just run on like heavier and heavier machines, right? That's one way you can actually do scaling. And of course, I'm not saying we could never consider this in the future to at least have like some sort of one-time bump to these requirements. But all of this for now is really the idea of like, imagine we really don't want to like change anything about the requirements of running an Ethereum node. How can we just get higher throughput out of the existing considerations? And what I'm trying to convince you about is that really, basically, the core of this is all about just better resource utilization. What do I mean by that? There's a lot of resources on Ethereum in these Ethereum nodes, like your CPU, your bandwidth, your disk, that either sits idle for a big portion of the overall time, or at least when it is used, is not used as efficiently as it could be. And that's really like the core of how you can get more scaling out of the existing hardware. I'll just go through a few examples. A lot of this is like more high-level schematic. It's not going to be like super correct in the very details. It's more going to try to give you an intuition. Also, don't judge me for these color schemes. I'm a bit artistically challenged. But so this is basically how the Ethereum slot looks today, right? You have 12 seconds in the slot, and the first 4 seconds of that are available for block verification. I call the rest empty. Now, of course, your node isn't literally sitting empty. There's a lot of very important work happening, but in terms of just the block verification, those other 8 seconds in the slot are empty. And then in the 4 seconds, you basically have 3 main phases. One is just propagation. You basically receive the block. Then execution, where as you can see, it's basically interleaved. I'm trying to use these 3 different colors. So like green, yellow, interleaved, compute, and disk, because sometimes basically you execute a transaction, you hit something you want to load, you go to disk, you load from disk. Of course, hopefully, sometimes you have prefetched it, but if not, you have to basically pause execution, go to disk. So it's like interleaved compute and state access. And then at the end, there's another compute step. It's a little bit different, though, conceptually from the other compute, which is the state root calculation that we also already heard about. So how can we basically just like utilize more here? I mean, one very obvious first thing is you see this empty space, right? Like we're only using a third of the slot. Well, we could change that, right? Again, we're not going to literally move immediately to a system that scales all the way to the full slot, but conceptually, you can imagine there's like a 3x, up to 3x first principles gain here. But just saying, look, let's try to find mechanisms to basically scale this up, use the full kind of 12 seconds or whatever, if we basically go to different slot times, use the full slot length for the verification. The 2 relevant features that will already like help move us towards that, or I guess yesterday we kind of decided to go with the one version of this, which is EPBS. EPBS basically, or any form of delayed execution, really like the one core focus there is basically the combination of slot restructuring and delayed execution, which basically this is really why that's exciting. That's really helping you stretch that processing to most of, not yet the full slot. That's more like the long term where we'd want to go, but like big chunk of the slot. What else can you do here? Well, in this picture, you're still doing these 3 things sequentially, right? You're first downloading the block, then you're executing, then you're calculating the state root. One ideal that you can try to move towards, again, you'll not immediately like be able to do that. That's actually quite hard to really like make sure that in the entire slot you can use your bandwidth and your compute and your disk in parallel throughout the full slot. But you can imagine that's the ideal way you would use these, right? You don't want your bandwidth to basically be sitting idle, quote unquote, at least from the block verification point of view, for like 2/3 of the process, and then you don't want your compute to only be useful in that portion and the disk only to be used in a small portion. You want all of this to basically run 24/7, ideally, right, in a node. How do we get there? Well, again, that's actually fully parallelizing. This is a bit trickier. There are some proposed features that already get us somewhere closer. So block level access lists, for example, are really interesting. They specifically let you parallelize more of the compute and the disk, because they pre-announce basically all the state that the block needs, so you can go start fetching this at the beginning while you already start the compute verification of the block. So that's actually quite exciting. Multidimensional metering, just a small kind of technical note there. It's actually funny. EVM is somewhat a bit complicated. If you just naively ship this, you don't actually scale the chain. Why is that? Well, because in principle, you could have a lot of compute and a lot of disk use now, because you can do them in parallel. But there's no way for users to consume both, right? Once you consume one, the block is filled, or if you want to consume both, you can only like, both of them are counted towards the same gas limit, so you're still basically back to the same old basket of consumption that you can do. So the nice thing with multidimensional metering, it has a similar name to the old idea of multidimensional pricing. It's much simpler though, so like no worries. It's basically just saying like, look, we keep the single one gas counter we have in Ethereum, but we basically start coloring it. So like every operation now contributes to both like basically like you keep track of like how much of the gas that it used was for compute, how much was for disk, and then you just have individual caps. You say, look, we now maybe have twice the gas limit, but you can only spend up to half of it on compute-related operations and up to half of it on disk-related operations, and that way now you can actually make use of the extra headroom that that feature gave you, right? So basically, like, again, you always have to think of not just how can you make it on paper run faster, how do you actually also expose that to the users. But again, all of these features would only be a first step in that direction. There's still a lot of like unclaimed territory that we'd afterwards have to find ways to unlock. Another example, here I wanted to first take a quick step back and talk about the work that we have been doing over the last few months, and especially like all of you EL devs have been doing a lot. Again, my visualizations today are a bit experimental. The idea here is that like the gray circle here is supposed to illustrate like the total available CPU in this case, because it's compute that you have within your like 4 seconds to verify a block, right? So basically like the distance from the center to the edges, and then these individual spikes are illustrating like how fast or slow are the different types of compute operations that you can do on Ethereum, right? So like that is different precompiles, different opcodes, other types of compute that you can use on Ethereum. And today it's actually quite annoying. Like there's a few of these really spiky operations. You can see like the one that's orange kind of highlighted here is the one that in this kind of example, that would be the binding one. You can't go any faster because this one is already at the very limit. But most of these actually have a lot of room to go. Like if you only want to do add operations in the EVM, you can fill the entire block. The entire block is still super quick to verify, right? You are not part of the problem, but still you're basically being artificially limited. So what we've been doing kind of as a loop, and again, this part of the loop does not actually require hard forks, is the clients have been running a lot of benchmarks to identify these like worst cases, and then you run this loop of, okay, you optimize, so like now the spike that used to be our problem spike got a little bit smaller. It's still not great, but at least it's no longer currently like a constraint in this picture. And then once you optimize, once you ship like an updated version of the client, you go and you scale the entire chain, right? So we started doing this. We went to 45 million on mainnet. We are preparing currently to go to 60 million, and that's exactly kind of coming from this type of iteration loop. But again, my talk is more focused on feature changes that help with scaling, and actually, this is quite laborious work, right? So you actually like there's a limit to like how much smaller you can make the spikes. There's a lot of operations that are actually like very non-spiky. So the actual thing that you'd want to do with a feature is what we call like repricing, right? You just want to make sure that all of these operations cost what they are supposed to cost, so that they're all kind of the same speed. And so that's basically like in this kind of picture language, that would basically try to make this picture much less spiky so you can scale it without going over the overall constraint of the system, right? And you can immediately see that basically, like, again, it's another example of just filling more of that kind of gray empty space that otherwise is useless. Now basically you could use much more of that. And we already have one EIP that's supposed to make the opcodes cheaper that are all basically overpriced, and then we will have another EIP that will make the precompiles more expensive. And so then hopefully we are getting close to that picture. Of course, we'll not hit it on first try. Probably like even after Amsterdam, the EVM will still be somewhat spiky, but then we can basically keep iterating, keep making it smoother. If you just do this naively, so this is specific. This specific is the example of compute, right? We're also doing this now with state pricing. That's a bit earlier stages. There's a lot of really good work ongoing with bloatnet. If you heard about that, that's not just focused on this work, but it's part of their scope. And we also like starting to look into this for data. It's a bit simpler story there. If you are not careful though, what you end up doing with repricing is you end up in this picture, right? So basically, like here you would have in a way had success. You basically homogenized the pricing for all of the compute, all of the state, all of the data operations, but you didn't pay attention to their relative pricing. So basically, like data, yes, there's no particular spikiness in there, but you're still basically overpricing data in this picture. So a block that would only consume data would basically like actually still be like relatively lightweight for the system. So basically, one important aspect of repricing is that you make sure that you actually also reprice relative to each other. And again, multidimensional metering here is very helpful for once you talk about several different resources. So that's another example. There's more, right? It's this recurring theme that basically like we just have this empty space that we really want to like utilize on Ethereum. EIP 1559, right? So 1559, it's a great way that Ethereum prices its usage, right? The base fee kind of mechanism on Ethereum. It has a few flaws. One, the most relevant one for scaling is actually that in order to, the chain always basically needs a signal of how much demand is there. So it basically always says that, hey, on average, you're supposed to use half of the block, half of the gas available, so that the chain can see if actually there's more than half consumed, oh, okay, we were underpriced, and if there's less than half consumed, we have to basically instead, we were overpriced, we have to lower the fee. This is great, this works well, but it does leave on average half of the throughput on the table, right? Like the average block, and if you run it over like 24 hours, a week, a year, like half of what you could have in terms of throughput already today in today's EVM, you're just leaving on the table just so the pricing mechanism gets a signal on demand. There's basically two ways to address this. The simple one is just making this problem less bad. You can claim a little bit more of that empty space by just moving the target away from this 50% mark. You could do 60, 70%. There are trade-offs, right? So basically, like the more you compress this, the more you squeeze out the kind of area where you get a signal for demand. But you really gain a lot of extra throughput, basically for free. And then in principle, that's not something we are short-term focused on, but in principle, you could like do a more involve kind of 5059 reform where you can maybe find a way to not be reliant on this kind of target underutilization at all. One more of these examples. This one actually is now zoomed more in. All of the other ones were basically like applicable to all different resources. This is an example of something that's only useful for a specific resource, in this case, compute. We've already heard about it in the other talks a bit. Basically, a parallelizing compute, right? Like your machine will have several cores, several threads. It's not, again, that they're all completely sitting idle, right? There's a lot of other things your node is doing. But it is not really being able to to reliably utilize, do multiple things in parallel for block processing. And that's maybe one thing that I didn't mention earlier. One important constraint on Ethereum, we always have to assume the worst case, right? We can't just price things for the average case, and it's in particular with things like transaction parallelization. There's a lot of really good work on optimistic parallelization, where you just hope that you can run them in parallel, that you can prefetch the state that they use, and then most of the time you're actually successful. But if someone basically tries to screw with you, they could create a block that makes you fall back to sequential processing. And so we always have to run the EVM at the speed that would still allow you to run safely at that lower throughput load. The idea here would be to really make sure that you can guarantee parallelization. The feature that helps there a lot is block level access list. It actually helps in two ways. Because it has the state diffs for the transaction, it allows you to run multiple transactions in parallel. Here, of course, the idealized version of you only have, I don't know, you want to run on 3 threads and you have 3 transactions. They're all equally long. You can run them perfectly parallel now. And another underappreciated aspect of block level access list is you can also run the entire state root computation. That used to be this extra section at the very end after you process the block. You can now run that in parallel as well, because you already know when you receive the block what the state diff will be. And you can, for example, actually one thing that I think we should explore more is you could start focusing on your compute on that while you actually go to disk to load all the data you need to then do the execution. So it's actually, that part is also really exciting. And again, it's just the otherwise empty cores that you didn't use are again, just extra resources that are available that we can't reliably use yet on Ethereum that we would unlock here. As I said earlier, it's not all just examples of take resources that otherwise just sit empty. There's also some examples of a resource is already used at its maximum, but you just use it smarter. And I just wanted to briefly, I didn't find good ways of illustrating this with silly graphics, so it's just text. But basically, because we saw a compute-specific improvement already, there's actually one bandwidth and one state-specific improvement, which is kind of nice. So we can make headway on all these fronts that come more from this direction of just efficiency improvement. So on bandwidth, that is what I don't know, I just call amplification reduction. So right now, on the CL side, where the block propagation happens, we're using gossip sub, and that has this amplification factor of roughly 8. So basically, every message you send on average 8 times, you receive 8 times. That's basically wasting, quote unquote, your bandwidth. how can you basically like just still use the same amount of bandwidth, but basically deduplicate without losing the propagation speed. There's some ideas there. They are not as advanced yet as some of the others, but basically like there's the proposal for gossip sub v2, which would basically just announce messages. You pull them, you can deduplicate that way at the cost of a little bit more latency. There's also ideas of using erasure coding so that basically you just send small chunks of the messages in the network, and then you can just assemble the message once you have enough chunks. Disk, the last example here basically is the example here that I wanted to bring in terms of more efficient usage is state load batching, right? So today, again, in the worst case at least, if you process a block, you just run the block, it does an S load, you stop, you go to disk, you get one value, you come back, you keep executing, it does another S load, you go get one value, you come back. With block level access lists, you know all the values, so you can go and much more efficiently just batch read the values from disk. So that should be another speed up there. And then the last thing I wanted to mention here is that actually, of course, very different time scale, as we talked about earlier, but the ZK EVM work is, in a way, like the ultimate example of just using existing resources more efficiently. People always focus on compute, because ZK, basically, at the very core, is like a compute compression mechanism. But it's actually like all three resources. That's the beauty of it, that it helps use more efficiently. It moves all the data, all the block data, into DA, into blobs. So whatever like multiplier you get in terms of you only have to sample the blobs, you don't have to fully download them. You get that all of a sudden now also for Ethereum mainnet throughput. So there's a big multiplier there. On compute, of course, you only have to verify the proof. And then on disk, you can now run stateless enabled by the ZK. So actually, like you basically like it really is like a huge efficiency gain there as well. So you can really think of ZK VM as like this example of like a huge just like improvement specifically on just efficiency of resource usage. A few caveats. Basically, if we zoom out here, as I said earlier, right? First, this was all just focused on full nodes and just block verification. There's many other operations, many other things we have to like keep in mind, where we have to make sure the performance is still good as we scale. So it's not as easy as just claiming that free real estate. An example that I think is especially kind of like illustrative here is RPC nodes, right? RPC nodes that basically like actually really kind of need to do very heavy other tasks as well. And in particular, ZK EVM is, I think, something where we have to like start preparing well in advance. ZK EVM is amazing for lightweight nodes that only want to follow the chain, but if you actually want to have some of that data, if you want to have some of the data, you still need to download it, and so on, right? So basically, like in ZK, basically, it really only have some node types, and we have to make sure that the other nodes still are performant as well. And then, as I said, all of this is only focused on in the moment. The chain becomes heavier and heavier over time as it grows. So what do we do about state growth? We already have some solutions that we're working on for history growth. You maybe saw that we recently dropped pre-merge history. And then also things like sync. There's many more of these. So it's not all just as simple as the picture I presented. But I really think at the very core of scaling is this loop of basically just making block verification faster. One last thing there. Also, as you basically get pushed closer and closer to the limits of what resources a node has, you are reducing your margin for error. So for example, there's now a work stream as well on like a CL side hardening of the chain, so that basically, because as the chain fractures, you have to like keep like rolling back and forward blocks and whatnot. And if you're already at the very limit of how fast you can go, like it's really starting to create problems. So that's another caveat. But really, if there's like two takeaways from this talk, I would say one is the timescales, right? Like we have these 3 different timescales on which we do scaling work, and they're all ongoing in parallel, both in the EVM and in the EF and outside. And then also the other big takeaway, I think, is really that on this like feature side approach to scaling, most of the unlocks really come from resource utilization. So you should really kind of think about kind of Ethereum scaling mostly through the lens of making better use of the available resources. And that's all. I think I have a little bit of time for Q&A. Thank you. And again, sorry for these graphics. It was a bit experimental.
Hi, Ansgar. Awesome talk. Thank you. I had two questions for you. The first is about the timelines you were sharing. You were sharing how the first one is super fast because these clients can do it on their own, and then the third one is super long because they're very hard, like cryptography problems. About the middle one, I think one thing that's kind of understated is the amount of consensus that's required for these three changes. The first one, like, there's not a lot of consensus required. It's usually a centralized company or foundation. For the third one, there's a lot of consensus required. And for the second one, there's a lot of consensus required as well.
Yeah.
Can you talk about how that impacts the timeline of the second one? Like, do you think it's feasible that protocol changes can happen on a predictable timeline because of like the factor of consensus? And then the second question is related to your slide on the bandwidth, this one. Oh, yeah.
Sorry, yeah, I'll go back to that.
Okay, the second one is on the next slide about the bandwidth, compute, and like scaling efforts. Given that you guys are trying to work within the constraint of like hardware, like we want Ethereum nodes to be able to run on like you shouldn't need to be like a company to run these nodes. Like people should be able to run these nodes at home. Given that Ethereum developers still have not come to consensus on what the minimum bandwidth and hardware requirements should be for a node, like how does that make these scaling efforts, like how does that impact how you guys know like by how much to improve scaling and the trade-offs when like you don't have a clear like agreement on like what the node requirements should be? Especially as you guys diversify like the type of nodes too.
Yeah, good questions. So
thank you.
The first one on the timescales, indeed, the top row here is a bit special because you can just do it. You don't have to like ask anyone for permission, which is great for iteration speed. I do think in the more recent past there have been a few examples on kind of Ethereum governance where I think we were a little too unfocused in a sense. Like it was just not clear like for what reason should we prioritize features. I personally think that's more a temporary side effect of the fact that Ethereum didn't really like have a clear kind of direction to go in. Basically, it was a lot of like one-off features that were just like nice to haves. I think as we are now kind of moving more into a kind of time again where we have like clear main priorities, scale the L1, scale the blobs, and improve UX and interop, I think that will actually help make most changes less contentious. I think basically in a sense, kind of like now the discussion around the Glamsterdam features is like the last time where we basically did not yet come out of a time period of already preparing with a specific theme in mind. My prediction, maybe a bit naive, would be that the hard forks after will be significantly more streamlined. Of course, timelines are always hard, not just in terms of the governance side of it, just the implementation overhead. So like here I assumed 8 months between different hard forks. Some people are trying to aim for 6. Some are more like thinking it's going to be 9. I don't know, I was trying to be somewhere in the middle. There's always some uncertainty around this. I personally think we are hopefully improving there. The other question in terms of no agreed hardware specs, there is, actually, there's this EIP 7870, which we basically like accepted on all codevs as like some sort of meta EIP where we said, okay, look, these are the specifications that you need to have so that we can guarantee you actually can keep up with Ethereum mainnet. Back when we decided that, there was more like a theoretical thing, so people like there was not super much attention. I think now as this becomes more load-bearing, as we scale and really push towards these limits, we will probably revisit those. Some of these might actually go a little bit down, some might go a little bit up. But I do think we will, there's no way around it. We will basically have to have some sort of reference spec for the minimum Ethereum machine, and I think we are already kind of basically there with that EIP. Awesome. I think I don't have time for more questions, so I'll be around for the rest of the day. Just come find me. It's an exciting topic. Let's scale Ethereum. Thank you.